All right, and we're moving on. What we have so far is that if you have a magnetic field and you place a charge in this magnetic field, so here's a magnetic field B, and if you place a charge in this magnetic field, whether it's positive or negative, doesn't really matter. As long as there's Q, and as long as this Q is moving at some velocity V, there's going to be a force, and you can determine this force using the following equation: F equals Q V cross B. The magnitude of this would be F equals Q V B sine theta. This is what we did last time, and in this specific case, force F would be pointing, you would use right-hand rule. Let's see, magnetic field points up this way, out of the page, yeah? Yeah, so the force itself would be out of the page, so I'm going to put here that force is coming out of the page. Now, what we want to consider is something similar, but now instead of a single charge, have a whole series of charges that will form a current. So suppose that you have a magnetic field that points like this. This is the magnetic field B, and then you place a wire in this magnetic field, then you actually run a current through it. So there's some current I. Maybe this wire extends and then connects to some battery here. Well, it should make sense that since you would have these charges here that would flow to the right, you would also have a force. And in fact, we did go over that already. So we know that there is going to be a force on this wire, and that this force will also point out of the page. At every location of this wire that is within this magnetic field is going to be force F. And you know how to determine that using right-hand rule. Now, there is an equation for this, and so the equation looks like this: F equals I, current I, times the length of the wire in the magnetic field, L times B. Well, I suppose what I'll do is, I'll do this. L cross B. Then if you want the magnitude, it would be I times L times B. So L is the length of, I is the current, B is the magnetic field, but L is the length of the wire that is within the magnetic field. And so in this specific case, that L would just be this. This would be L, right? This wire could extend, the wire could continue to the left for a while, it can continue to the right for a while. So the whole total length of the wire would be something bigger than this L, but the L that we need for the equation is simply the length of the wire that is within the magnetic field. I'm going to put this on the side. All right, comma L length of wire in the field B. All right, now let's see, let's just quickly derive this thing so that we know where this comes from. This equation here, we will use that. So let's consider the case where we have, here's a wire, here's a current, and then I have a little bit of a charge here. This is a little bit of Q. I guess I could call it dq, but I won't do that. This is Q, and then there's another Q, and then there's another Q, and then there's another Q, and all of these Qs flow with speed V to the right. We have Q, and then another Q, and then another Q, and then another Q, and all of these Qs comprise the current I, and everything here is happening within a magnetic field. So let's add the magnetic field, do it in blue. Let's add the magnetic field to the picture. So B points up, B points up, and B points up. All right, well, let's use this equation that we have here. So F equals Q times V cross B. I'm considering force on a single particle, and I can figure out that this force here will just point out of the page. So this is force F. But I don't want to limit myself to one Q. I want to figure out the force on the whole wire, the total force. So what I'm going to have to do is I'm going to replace that Q with the following. See, I is defined as dq over dt. I'm going to assume, I'm going to simplify my life a little. I'm just going to say that the current is steady, and so I can replace this with averages. So I have some delta q over delta t, and I'll go even farther and I'll get rid of the deltas, and I'm just going to put q over, so t is some time, and within which the charge takes to flow from this point to say maybe this point. Right, so this would be the time it takes for that charge to flow from this point to this point, and so now I will have a current produced by this single charge, and then let's see what we do with that. So let's replace this Q with I times T times V cross V. But now V, the velocity of this charge, that's just the distance covered over the time T. Now the distance covered, we'll label that as L. So the distance covered here, that's just going to be L, length L. I should have really chosen should have taken a whole length of the wire within the magnetic field. So let me do this. I put that here. I'm going to get rid of, not that it matters too much, but it's a little clearer to see it this way, I think. Right, so we're going to consider this length L to be the total length of the wire within the magnetic field, and I think that'll be better. So this is L over T. All right, and so that would also imply that if I want this thing to be a vector, then L would point in the direction of the velocity, the direction of the current. So I could say here that L is parallel to the velocity of the charge, which also means that L is parallel to the current I. I could put vector above this current if I wanted to. That's fine. I think I need to. So then what I get out of this is that the force equals I, the magnitude of the current, times T, the time it will take for the charge to flow through the magnetic field, times, well, V, but V is going to be replaced with L over T crossed with the magnetic field, and now T nicely cancels out, and I have the equation I wanted. So F equals I times L cross V. And of course, this equation, if you understand it well, you can easily replace this with F equals L I cross V. Reason being is that L and I are parallel. So in this case, I'm using the magnitude of L, but I as a vector. In this case here, I'm using the magnitude of I, but L as a vector. Either equation will work. And of course, they both amount to, when it comes to defining the magnitude, F is just ILB. Well, it's really ILB times the sine of the angle theta, where the angle theta would be the angle between I and B. I and B vectors. So I should really add sine to this. And then I have a complete equation here. So suppose that I have a picture that looks like this. Let's say that this is the magnetic field B. Right, so magnetic field points like this in this direction, and then I have a wire, and the wire runs like this, and the current flows in this direction. Well, in that case, length L is the length of the wire in the magnetic field, so that would be this. Right, this would be the length L. And the angle theta would just be this, angle theta. And then current I is whatever it is, magnetic field is whatever it would be. All right. Let's solve a problem with this. So I'm going to move up. I'm going to redraw the situation just so that we remember what it was when we have a magnetic field that points in a certain direction, and then we place a wire within this magnetic field. So here's a wire, and then there's a current that flows through it. Here's the current I. I can calculate the force by doing the following: I times L cross B, which is going to give me the magnitude of I, L, B sine of the angle theta. L is the length of the wire within a magnetic field. So in this specific case, the length of the wire within a magnetic field is just this. Now let's keep this on the side here. The angle theta is the angle between I and B, and so in this case, this is the angle theta. It just so happens that the way I drew it, it's 90 degrees. But all right, let's keep this on the side, and let's try a problem. So here's a simple one. This is on page 826. It's number 34. It's in the algebra-based physics book, but it's easy to deduce from the context of what's happening in the problem. So you have a magnetic field that points to the right like this. The size of the magnetic field is 2.5 Tesla, so it's a uniform magnetic field of 2.5 Teslas, and it points in the positive x direction. And then you have a wire that runs like this. Let's use black. You have a wire that runs like this, and there's a current in it. And the value of the current is 15 amps, so this is 15 amps. The angle theta is given. Angle theta is given as 30 degrees, so you have 30 degrees here, and we need the length of this wire. It's 3 meters, so L is 3 meters. Now that L, that's this distance here. Right, so this is L, and that L is 3 meters. That's the picture we have, and the question is, what is the force acting on this wire? So F is the question mark. Let's calculate the magnitude of this F, and so F equals I L B sine of the angle theta. Let's plug in the numbers. Current is 15, length is 3, magnetic field is 2.5 times the sine of 30. Sine of 30 is a half, so what you're looking at is 45 times 2.5 times a half, and then you can multiply this out and you get what you get. So let's see what we get out of that. We have 45 times 2.5 times 0.5, and for this we get 56. It's good enough. So 56 newtons. That's the force. Now, in which direction does it point? Well, you would use the right-hand rule, and in this specific case, you would have your fingers. So from the right-hand rule, you'd have the fingers that point in this direction. You'd align your fingers pointing in this direction. And then the thumb of your hand has to point in the direction of the current, so it points like this. Right? And remember, this is a right hand. So the only way this can work is if the force is pointing into the page. And so I'm going to put, for the force, maybe in white, I'm going to put X here, and this I'll put it along the wire. X, so the force points into the page. Force is into the page. That comes from the right-hand rule. E, I, and the force must be coming out of the palm of your hand pointing into the page. All right, well, so this will do for this part, for the force, magnetic force on the current that is placed within the magnetic field.